Hello, my name is Lydia Spychalla, and I will be presenting to you the research that I did over the summer to implement an equation of state that conserves baryon number, strangeness, and electric charge. So the motivation from this project comes in wanting to extend current relativistic hydrodynamic models of quark-gluon plasma to be able to conserve these charges Bs and Q and study high density regions of the QCD phase diagram in a more robust way. So currently, you see in figure 1, the QCD phase diagram is shown. So we have experimental data that explains how quark-gluon plasma matter exists in high temperature and low density regions of the diagram. And we have observational data from neutron stars that explains how the matter exists in high density and low temperature regions of the diagram. So, we're particularly interested in studying the phase transition between quarks and gluon, or quark-gluon plasma and hadron gas, and studying the critical point of that phase transition, which is in the high temperature and high density region. And so the relativistic hydrodynamic models that we have match experimental data really well at this low density regime. But if we're able to implement these conserved charges of Bs and Q, we'll be able to study the totality of the phase diagram more accurately and search the regions closer to the critical point for critical behavior in our simulations. So the goal of my project was to create a code that maps a given temperature and set of chemical potentials to these different density profiles, baryon density, strangeness density, and electric charge density, and to also produce an inverse mapping that, given a density profile, could tell you where the temperature and chemical potentials of that point in space are on the phase diagram. So to do this, the code that I produced does an interpolation over a 4-dimensional equation of state, which provides gridded values of Bs and Q, as well as energy, entropy, pressure, and speed of sound. And so it interpolates over all these values to provide a smooth mapping between the temperature and chemical potential and the density profiles. And then to produce the inverse mapping, we do root finding over this interpolation to be able to find, given a density in a baryon, strangeness, and electric charge density, we can say where in temperature and chemical potential this point falls. So we were able to test our code using the Ising heavy ion collision model, which produces an initial condition of these different density profiles. So we were given a region of space that each point has a baryon density, a strangeness density, an electric charge density, and we were able, and an energy density. And we were able to root find over this interpolation and map it back out into temperature and chemical potentials. So in figure 3, you see the result of this. So some things to note is the mappings that we did produce a very expected value for an expected profile for a heavy ion collision. The temperature is, the temperature regions that are covered are very similar to what we see experimentally, and they're symmetrical to the different chemical potentials. So now that we have a code that can do this mapping between temperature and chemical potentials and the densities, we are able to integrate this into the hydrodynamic simulation code so that this will be able to be done mid-simulation in converting between the equation of state and the needed hydrodynamic variables. So now that we do have the ability to run this code in the high density and high temperature regions of the QCD phase diagram, we will be able to see for the first time what these regions seem to behave like in the models that have already been proven to work very well at low density regimes. And so we will be able to probe these higher regions of the QCD phase diagram for critical behavior. And I want to thank the Daring Butts Foundation Scholarship for providing the funding for this research, and members of the UIUC Nuclear Theory Group for their support this summer. Thank you.